Homework 14, we're going to be concentrating on the acids unit that we did. And we've also got a couple of calculations in there as well. First off, we've got some straightforward general equations here, neutralization, and what's produced. Now, when an acid reacts with an alkali, a salt and water is always made. And so that is the type of equation we want for each of these. Now, if you can't remember them, you have to go back to the acids unit, and I think you have to find them. I can't give you any more hints other than saying that salt is obviously going to be in the a product for every one of them. But what else is made? Everyone is slightly different. A couple are the same, but go back to the acids unit and look at those if you're not sure. They're all examples of neutralization. Told you that already. The acid is neutralized in every one of those to make a salt. And we've got some examples here. Let's say I was to do calcium hydroxide and hydrochloric acid. Okay, what would the products of that be? Well, first off, the salt. For the salt, the metal. Okay, the metal gets taken across to the salt. So every one of these, there's a metal in them. The metal gets taken across to the salt. So on this side, we would make calcium. So the salt is going to contain calcium. Now, hydrochloric acid always gives us a chloride. Sulfuric acid always gives us a sulfate. Nitric acid always gives us a nitrate. So the chloric is going to make chloride. So there is our salt. Okay, so the metal essentially comes from the base. The non-metal comes from the acid, and a salt is made from a metal and a non-metal. Okay, so it's calcium chloride plus water. Okay, so can you give me the products for each of these? Next question, and this one is particularly interesting. It says, sketch a graph showing how the pH of hydrochloric acid would change as calcium oxide were added to it. Explain why the pH doesn't rise in a proportional manner. Okay, this is a core practical, so it's essential we know about this one. And at the start of it, we've got acid in a beaker, so that would be a pH of 1. And I always ask students, as we add the alkali, calcium oxide, when it's in water, it's an alkali. As we add the alkali, what will happen to the pH as time goes by? And everybody says, when they're at the start, they just expect the pH to rise in a nice gradual proportional manner, straight line manner. Proportional is a straight line manner. And it makes perfect sense, but of course it's all wrong. So what we're going to try and do is explain why. So I'm just going to sketch an apparatus out now. This isn't the apparatus we use to do this practical, but we could use a burette. Okay, so now I want your answers to this question. I want your answers in your own words. I don't want you to copy what I'm doing now. This is just to try and help you understand it. Okay, so that's a burette. Now in the burette, let's just say we filled the burette with alkali. Okay, because we're going to add, in this core practical, we added alkali to the acid. In the beaker at the bottom here, okay, I've got my acid to start with. Now, let's just imagine my acid particles look like this. Okay, we happy with that? And can we imagine in my burette, okay, my alkali particles are hollow looking. Are we happy with that? Okay, so when we add the first bit of alkali, so we open the tap at the bottom here, and the alkali runs into the burette so that the liquid level will go down. Okay, let's just say I've added that alkali particle. That alkali particle is going to neutralise, it's going to react, it's going to be a chemical react with that acid particle, and it's going to make a particle over here now with those two combined, and that's going to have a pH of 7. That particle there will have a pH of 7. So that alkali particle that was up here is now in the beaker and has reacted with an acid particle. So those particles, those solid ones with the acid and the hollow ones with the alkali. Okay, so there was this up here, we had a pH, say, of 14. And here we've got a pH of 1 to start with. Okay, but as time goes by, the acid's going to neutralise the alkali. Now, that particle there has got a pH of 7, but there's still lots and lots of acid particles left. And so the pH of the whole thing stays at 1. Okay, it doesn't rise. Now let's explain that a little bit more. Okay, because to explain that a little bit more, we have to understand how pH changes. Now, the more hydrogen ions in solution, these are hydrogen ions. The more hydrogen ions in solution, the greater the pH. Now, you might be saying to me right now, but we've just taken one of those hydrogen ions away, so why hasn't the pH risen? And that's a very, very good point. Okay, so to try and understand that, okay, we're just going to imagine in this beaker, we have, let's say we've got 3.5 million. Now, there's going to be many, many more than this. I'm just picking a number that's quite easy for me to write and say, if I'm honest. Okay, so there's 3.5 million hydrogen ions at the start of this. Now, when we added that first, say, centimetre cubed of alkali, let's just say we added 1 million alkali particles. Okay, now those 1 million alkali particles are going to neutralise 1 million acid particles. Okay, let's just say that. So to work out how many acid particles we've got left, we need to subtract them. So 0 minus 0 is 0, and all the way up here, all these zeros minus 0 is 0. So that 0 minus 5, that doesn't work, so we need to cross that, make that 2, carry 1 over 15. Sorry, to put 10 there, don't we? So that's going to be 5, and 1 minus 3 is going to be 2. Anyway, either way, we've got 2.5 million, okay, acid particles left. Okay, so adding that first bit of alkali added a load of hydroxide particles, and they neutralised a load of acid particles, but we've still got 2.5 million left. Now, you may say, well, that's decreased the hydrogen ion concentration. Yes, it has. Okay, but what you have to remember with pH is pH only rises by 1 point when the hydrogen ion concentration is decreased by a factor of 10. In other words, have the number of zeros changed. Okay, so we've got 1, 2, 3, 4, 5, 6, 7 numbers there. Here we've got 1, 2, 3, 4, 5, 6, 7 numbers. Still got the same number of zeros after the initial number. So the hydrogen ion concentration has not decreased by a factor of 10. So the pH remains absolutely identical. So let's add another load of hydrogen ions. So we're going to run some more of these alkalis, sorry, add some more hydroxide ions. We're going to run some more of these hydroxide ions. The burette levels dropped again. Okay, and this time, there we go, we've added another one, and it's neutralised some more. Okay, so let's add, let's say we've added exactly the same number, so we've added another 1 million hydroxide ions. So they've neutralised a whole load more hydrogen ions. Let's subtract those. Okay, so we've got now 1.5 million hydrogen ions left. And you're saying to yourself, well, that's loads less than we started with. And it is, you're right. But again, we still haven't changed the pH from this original number by a factor of 10. Okay, there's lots less, but there's still the same number of zeros, if you like, after this initial number. So the pH remains 1. So we start to get a graph looking like this. Let's add another one. Okay, let's add another load of hydroxide ions. So the liquid level in the burette's going to drop even more. Okay, down to there now. Okay, and we're going to add another. Say 1 million hydrogen ions. Okay, so let's subtract those two. Now this time, okay, when we subtract 1 million from 1.5 million, we're only left with 500,000. Right, now we've got to change, haven't we? So now we've lost a 0, if you like, from this number. So we have now, okay, decreased by at least a factor of 10. So when we decrease by a factor of 10, the pH rises by 1 to there. Only a tiny bit. Let's add another alkali. Run that one in. That's going to neutralise. So we've neutralised loads of these now, haven't we? So when we add another alkali, it's going to neutralise the last acid. Okay. So let's add another exactly the same amount of hydroxide ions. Okay. So we're going to neutralise the last 500,000. Okay. And we're now going to have, and there's going to be 500,000 left over. So that's, so there will be 500,000 now hydroxide ions in excess. So we've now got spare hydroxide ions. And let's draw that one in there. There it is there. My hydroxide ion all on its own. Okay, so now the pH is no longer acidic because all the acid has been added. Indeed, we've gone past the neutral point. Okay, we went past the neutral point. In fact, we went straight past the neutral point, and now we've got excess hydroxide. We've got 500,000 hydroxide. So that's going to rise the pH past neutral. So it's gone past, it went straight past neutral. Okay, because it was neutral when we added 500,000. But then we kept on adding. We added 500,000 excess. So that's going to rise the pH all the way up to 13 if we use the same logic. So the next point is going to be up there. Okay, so we've got all these zeros of hydroxide ions. Okay, now if we add another 100,000 hydroxides, we now got 1.5 million hydroxide ions in excess. Now that only changed the number of hydroxide ions in excess by a factor of 10, so this time that raises the pH to 14. And it carries on like that. So there's our pH curve. Quite difficult to understand, okay? So an explanation here is a simple explanation, something along the lines of, when we add alkali to the acid, only a small number of hydrogen ions are neutralised. There is lots and lots of hydroxide ions left over, so the pH remains low. Only when the concentration of hydrogen ions changes by a factor of 10 does the pH start to rise. We quickly add an excess of hydroxide ions and the pH rapidly rises past the neutralisation point. So just a brief explanation. Have a go. It doesn't matter too much if it's right, but can you get something in your explanation along the lines of pH only rises by 1 when hydrogen ion, H plus ion, that's the hydrogen ion, concentration decreases by a factor of 10. Okay, so if you can get that into your explanation, that would be great. See how you go. What mass of carbon dioxide is produced from burning 3,200 grams of methane? Okay, well, I'm not going to do methane. You can do that one anyway. I'm going to do a different experiment. I'm going to do one with ethene. Ethene reacts with 3 oxygens to make 2 carbon dioxides and 2 waters. Okay, so with these questions, first thing I want you to do is decorate the equation. So 3,200 grams of methane. So 3,200 will go on the methane there. And the question mark is what mass of carbon dioxide. So you put a question mark on the carbon dioxide, cross that out, cross that out. Okay, well, I'm not going to do that. I'm going to say I'm starting with 14 grams of ethene. Okay, and I'm going to ask, my question is going to be what mass of water is made. So I'm going to cross out the oxygen and cross out the carbon dioxide. So you do that first. 3 stages to all these calculating quantities. First stage, moles. Second stage, stoichiometry. And third stage, moles again. Okay, so let's have that labelled up. 1, 2, 3. Okay, so moles equals mass over MR, formula mass. Well, the mass is grams there, so that's 14 grams. Now you need to work out, I need to work out the MR, the formula mass of the ethene. So you work out the formula mass of whatever you wrote the mass under. You'll do it for methane. I'm going to do it for ethene here. So I've got 2 carbons and 4 hydrogens. Well, carbon is, oh, blimey, there's a typo there, isn't it? Carbon is 12. I need to change that. So that'll be changed in your book when you see it. Carbon is 12 and hydrogen is 1. So 2 12s are 20. Sorry, 2 12s are 24 plus the 4 hydrogens is 28. 14 divided by 28 equals half a mole. You need to work out the MR, the formula mass of methane, 1 carbon and 4 hydrogens. You work out how many moles you've got. Right, stoichiometry. Now we're looking at the big numbers. In my equation, I've got a big number 1 there. There's no number before the ethene, so there's a 1. And I've got a big number 2 before the water. So I'm going to write 1 here, ethene, C2H4, makes 2 waters. So how do we get from 1 to 2? Answer is we had to multiply by 2. So that's a doubling relationship. So I'm looking at the relationship here in the stoichiometry. Okay, I don't start with 1 mole. I start with half a mole, so 0.5. that was multiplied by 2. To get from 1 to 2, we had to multiply by 2. So I need to multiply by a half by 2. So by 2 again. Half multiplied by 2 is 1. So in my second stage here, I've got 1 mole of water. If these numbers were the same, so if that was 1 there and that was 1 there, I would have a half a mole of water because they're the same relationship. So we're just looking at the relationship. Okay. In my example, it's doubling. Where you see in your example, there's a 1 there and there's a 1 there. So it's the same in your example. Okay. But in my example, I've got 1 mole of water. So stage 3, moles. Again, so we need to rearrange the moles equation. We need to rearrange the moles equation. Moles equals mass over mR to make mass the subject. So mass equals moles times mR. Now we now need to calculate the mR of the product where the question mark is. Okay, not 2 waters because I always say if you've got a twin, you don't have to get your twin standard scales with you to see your own mass. That's the big number is a stoichiometry number. That's stage 2. So it's just water, just H2O. Well, hydrogen is 1. Oxygen is 16, so 2 1s are 2 plus 16 is 18. The forming mass of water is 18 times my 1 mole from over here. That's 18 grams. Okay, you're obviously going to have an answer somewhere in the thousands, I would imagine. Exactly the same. 1, 2, 3 stages. Final bit. An ink spot around 34 mils on filter paper. Solvent around exactly 6 centimeters. So what is the RF into 2 decimal places? Well, you divide the ink spot by the solvent. Now look at the units, check the units. You've got to get the units the same. So I would convert that to millimeters if I were you. Okay, the answer has to be less than 1. The answer is a decimal. Answer less than 1. If it's not, you've done it the wrong way around. Okay, I'm just running out of time here. What is the formula of a compound made of iron 3 ions and hydroxide ions? Well, let's imagine we're doing chromium 6 phosphate, okay? The Roman numeral tells us the charge. So if I was doing chromium 6 phosphate, that would be Cr6+, and the phosphate ion, you don't need to know the phosphate ion, but the phosphate ion has a formula PO4 3-. Positives and negatives have to be the same. Okay, so I would need more negatives, so I need a whole nother phosphate ion. So to have 6 minors to balance out that 6 positives. Therefore, the formula of that one will be CrPO4 close brackets twice. Okay, have a go at that one.